All right, so today we're doing problem 3075, maximize happiness of selected children. Kind of a morbid problem description, right? It's a little bit strange thinking about trying to maximize the happiness of only selected children. Can't we just make all children happy? I don't know. Okay, so this is a medium. Now, like most people probably realize at this point, the classification isn't always super indicative of the actual difficulty of the problem, right? There's mediums that are harder than some hards, and there's mediums that are equivalent to easies, okay? But with that said, let's go ahead and get right into this. So you are given an array happiness of length n and a positive integer k, okay? There are n children standing in a queue where the ith child has the happiness value happiness I, okay? So each child has an intrinsic happiness to them, okay? You want to select k children from these n children in k turns. All right, so I can literally choose k kids. That's all that basically means, right? There's n children, and I'm going to choose k of them. All right? In each turn, when you select a child, the happiness value of all the children that have not been selected till now decreases by 1. Okay, that kind of makes sense, right? You remember, like, waiting to get picked in line as a kid, and if someone didn't pick you, you're like, oh, man. Right? So every time you pick a kid, all the other kids get a little more sad, I guess, right? They get a little sadder. Note that a happiness value cannot become negative, and it gets decremented only if it's positive, right? So the minimum happiness someone can have is 0. If your happiness is 0, right, you're down in the dumps and no one picks you, you don't become -1 happiness. You just stay at 0, all right? So we're going to want to return the maximum sum of the happiness values of the selected children you can achieve by selecting k children. Okay. So for this example, right, we have happiness equals 1, 2, 3. All right, and we have k equals 2. And, well, if I'm trying to maximize my score, then obviously I'm going to pick the max person, right? So I'm going to get +3, which is going to result in everybody else decreasing by 1. So this will become 0 and 1. And then, obviously, again, since I'm trying to maximize my score, I'm going to select the max person and get +1, equaling 4. And that's why the answer equals 4. All right, maybe another example. Here, k equals 2. So you choose to make the 0 case interesting. Right, we have a bunch of kids that are equivalently happy. I choose the maximum one, which gives me +1. Now everybody becomes, everybody gets decreased by 1. So now everybody has a happiness of 0. I choose a 0 plus 0 equals 1, which is why this is 1. Okay, 2, 3, 4, 5. I can only choose one person, so I choose, again, the maximum person. Hopefully that's pretty intuitive. Right, so if we want to maximize our happiness score, we keep picking the maximum person. Maximum child, I guess. Right? So that's like the only observation here that's really important, right? We should always pick, for k children, we should pick the k largest children. Okay? So that seems pretty intuitive, right? Like if I want to maximize the happiness, well then keep picking the kid that's the happiest. So that might lead you to think, okay, well maybe we should likely, we're going to take happiness and we're going to sort it. Right? We're going to sort happiness because, well, we want to pick the maximum person, right? So we want to keep track of who the maximum person is and take those people out accordingly so that we can maximize our score. If we want to have the happiest score, pick the happiest kids, right? Now, I guess the only little stipulation, right, the only thing that makes this, I guess, a little bit tricky is that, well, every time we pick somebody, everybody else becomes a little less happy. And you're wondering, well, is that going to affect this sort idea? And the truth is, no, it's not. Because, whatever your initial sorting system is, right, if you have let's just say generally you have a system A, B, C, D, E, F, right? Now, in an ideal world where there's no removal, right, if you were going to choose K equals 3 kids, you're going to choose these 3, right? You're going to choose the largest 3. Let's assume that the system is sorted. right? But you might say, well, now that I'm playing this game, you know, every time I pick someone, things are going to get smaller. Yeah, but everything gets smaller uniformly, right? So even though this system's already sorted, if you have A minus 1, then B minus 1, then C minus 1, then D minus 1, and E minus 1, and you already selected F, well, it's still going to be the same, right? If, like, imagine it like this, right? If you sort all your friends by height, okay? So you have everybody that is their height, and then you make everybody 1 inch shorter. Well, it's still going to be the same order because you basically pushed everyone down together, right? So if you're like this, and then you get pushed down 1 inch, well, you're getting pushed down together. So this sorted system is going to maintain its sorted system. So who's going to be the next best person? It's still going to be E minus 1, right? And then after this, you're going to have A minus 2, B minus 2, C minus 2, D minus 2. But yet again, since you pushed everyone down uniformly, the happiest kid, regardless of the fact that this kid is getting sadder because you're not picking them, right? They're getting minus 1 unit of happiness, minus 1 unit of happiness. Regardless, they're still going to be the biggest happiness that you can choose, right? Even though you've developed a bad relationship with them because you're not picking them, they're still going to be the happiest one left, right? So this initial ordering is all that matters, right? The fact that the system is initially ordered doesn't change the fact that the initial order doesn't matter. And the fact that someone's happiness is subtracted from them, since it happens uniformly, it's not going to affect the overall happiness, right? It's not going to make that person less happy than the person before them, right? If I'm taller than you and we both lose 1 inch, I'm still going to be taller than you, right? If we're all aging at the same rate, when you're older than me, you're always older than me, right? Because the rate of which it's changing is the same, right? So the rate of which these happinesses are changing is the same. So then the happiness is the ordering is going to maintain the same. So the best person is still the same. That's pretty much the point. Okay, so then how are we going to integrate this into a solution? Well, the idea is then we can just pick the happiest person, and notice that every time we pick somebody, the new happiness of the person before us goes down by 1. Right? So every time I pick someone, the subsequent person is going to lose 1 unit of happiness for the person that I picked, right? So if I've picked already 2 people, that means that for the third person, there's going to be minus 2 happiness, right? After I've already picked the first person, the second person is going to automatically have a negative 1 attached to them. After I pick the second person, the third best person is going to have a negative 2 attached to them. When I pick the fourth person, I've already picked 3, so whoever the happiest person is going to have a negative 3 attached to them, right? There's some negativity associated with that person because I've already picked them, right? So what I can basically do is I can look at the happiest people in range K. I'm not going to do it this way. I'll just do it right directly in the code, and you'll see what I'm doing to make this work to get these ideas. But that's pretty much the idea of this problem, right? It's not super difficult. Okay, so we're going to have res be the happiness score that we're going to return. Now we need a sort happiness. Now I'm going to do it in reverse so that the happiest people, right, the people with the largest value are at the front instead of being at the back. Okay, and then I'm going to choose children in range K, right? There's K children I'm going to choose. So when I choose the first person, who am I going to choose? I'm going to choose the first person in the array. Can't spell, I guess. All right, so I'm gonna choose the first person in the array and add that to res. Right? Now this is gonna fail because I'm not accounting for the fact that people become less happy, right? This is 5 because I choose the 3, then I choose the 2. Right? So I choose 3, then I choose 2. But the second person's happiness is actually only gonna be 1 because the amount of people I've already chosen, which is conveniently I, will be subtracted out, right? So basically, I choose that person, and then I represents the index that I'm at, right? So if I'm at index 1, I'm choosing the second happiest person, and the second happiest person will have to get subtracted 1 because I've already chosen somebody, and that corresponds to the index that I'm at, right? When we look at this, right, and we look at, I don't know, a system like 5, 3, 3, 1. Well, in terms of indexes, this is index 0, 1, 2, 3, right? And when I choose this person, there's They're the happiest person. I haven't chosen anybody yet, so they don't get anything subtracted. After this, everybody gets 1 subtracted from them, right? When I choose this guy, he gets 1 subtracted from him, so everyone else gets 1 subtracted from them. Right, when I choose this guy, I get 3 subtracted from him, and everyone else gets 1 subtracted from them. And when I choose this guy, I get 2 subtracted from them, and everyone gets -1. When I choose this guy, 3 subtracted. And look at that. That corresponds to these indexes, right? If I just subtract this value, it's equivalent to the values below. Does that make sense, right? This -1 is equivalent to this -1. This -2 is -1, -1, -3, -1, -1, -1. Right, so I can just use the index because the index represents the person that I'm grabbing, and it also captures how many people I've already grabbed, right? Now, this will fail because at a certain point, when I go through this system, right, like here, when I choose 3 people, right? So when I choose 12, 1, 42, I'm going to sort it, 42, 12, 1. Right? When I choose 42, everyone else will get -1. When I choose 12, everybody else will get -1. So this will be 42 plus 11 plus, well, this is going to say that it's -1, right? Because 1 minus 1 minus 1 is -1. But remember, the minimum is 0 because at a certain point, someone might be waiting so long that they were happy, but then they keep getting, knocked down because they're not being selected. And so they end up going to 0, but they don't go to -1. So this is supposed to be 42 plus 11 plus 0. So at a certain point, it might not work out anymore, right? This person is just too sad. So if they get less than 0, we don't want them, right? We just say 0, right? We waited so long to select you that you no longer have any happiness, and now it's going in the negative territory if we continue to minus, but the minimum it can be is 0, so just add this in to capture that. Okay, so what is the space and time complexity of this problem? Okay, so let's say n is the length of happiness. Right, so the time, we have to sort happiness, right? So that's n log n time to sort. And then we look at a range of k. Right, but k can never be greater than n because you can only choose as many people as there are. So k is less than n, and k is less than or equal to n, and n is less than or equal to n log n. So it's O(n) of log n. For space, well, let's imagine we sort this in place, and then we just update this variable. Okay, so this is in place sort like heap sort, so that'd be constant time. And then we just update a variable accordingly, so that's O of 1. All right, guys, hope you have a beautiful rest of your day.